Imagine trying to manually catalog every single detail of a complex 3D object, like this fracturing stone polyhedron. If you try to track every single flat panel and sharp corner by sight alone, human error is almost guaranteed. You will miss a hidden line. But there is a mathematical check you can run to prove your manual count is 100% accurate. Looking closely at these solid wooden blocks, we can identify the three distinct components that make up any polyhedron. First, we have the faces, the flat 2D surfaces that form the outside of the shape. Next are the edges. These are the rigid structural lines where two flat faces meet. And finally, we have the vertices, the exact corner points where multiple edges intersect. By tallying those three variables, you can plug them into Euler's formula: faces plus vertices minus edges. If you've mapped your shape correctly, the physical geometry will always balance out to exactly 2. Let's test this methodology on a standard baseline shape, the cube. On this 3D wireframe, we map the 6 outer surfaces, giving us 6 faces. Next, we count 4 corners on top and 4 on bottom, 8 vertices. Finally, tracing every border gives us 12 distinct edges. We run the calculation: 6 plus 8 minus 12. The result is exactly 2. Because the math balances, we have absolute proof that we didn't miss a single component or double count a line. Now let's apply the exact same checklist to a shape built from irregular, multi-sided polygons, the triangular prism. We map 2 triangular bases and 3 rectangular panels, 5 faces. Counting points on the front and back bases gives 6 vertices. Tracing the solid framing and hidden backlines totals 9 edges. We plug in 5 plus 6 minus 9. The equation balances to 2. Euler's formula does not care if you mix triangles and rectangles together. The underlying physical relationship remains constant. For our final test, we need to evaluate a shape where the lines drastically converge to a single point, the square-based pyramid. This wireframe has a square base surrounded by 4 triangular panels, 5 faces. We count 4 corners on the base, plus the top apex, 5 vertices. Tracing the 4 baselines and 4 slanted lines gives 8 edges. Final verification: 5 plus 5 minus 8. The answer is 2. From basic parallel boxes to sharply converging pyramids, this strict accounting methodology guarantees 0 structural errors. Reviewing our 3 distinct geometric models side by side, you can easily verify the results. Despite their vastly different shapes, the data tallies perfectly balance the equation every time. When we evaluate real-world physical objects, like this collection of solid, dark, and gold polyhedrons, we rely on this exact math to verify their structure. If your final tally ever results in anything other than exactly 2, an alarm should go off in your head. It means you have definitively double-counted a face or missed a hidden edge. Grab a piece of paper, sketch your own complex polyhedron, and test this universal law for yourself right now. And if you want to see more geometric workflows, make sure to subscribe.